We shall be looking at standard form in this lesson. And getting the standards, it can be a confusing topic for some students, especially when they calculate and get the final result and they need to express that result in standard form, or in calculation the figures are in standard form and they don't know how to go about addition, subtraction, multiplication, or division, all in standard form, or even to express standard form to ordinary numbers. Well, this lesson is specifically tailored to tackle those problematic issues. So take your time, watch, take notes, listen, and you'll be taking through those processes. And by the end of the class, you shall be able to do those activities or maths on standard form. So let's start. Standard form was developed by scientists to enable us to write very large numbers and very small numbers in little spaces. So it was a way of writing large numbers and small numbers in little spaces, and it has a notation. So we're going to look at very large numbers in this first video. Very large numbers, which means positive power. Okay, so now let's look at what we have this table. It's a number, ordinary form, and standard form. So this is the ordinary form that we are used to, and this is the standard way of writing it. So we call it the standard form or scientific notation, because this standard form is basically used by scientists, or is used frequently by scientists. Yeah, that's the way they represent large numbers. So you usually see figures written in this form than they are written in this form in scientific writings and notations. So 2000 in ordinary form is 2000, but in standard form it's 2.0 times 10 raised to power 3. 8 million, this is how it's written in ordinary form, but in standard form is 8.0 times 10 raised to power 6. 1 billion in ordinary form, and in standard form is 1.0 times 10 raised to power 12. 185, 185 in ordinary form is 185. In standard form is 1.85 times 10 raised to the power of 2. Now, how do we write in standard form? How did they get to this? How can, it was written, this was the ordinary form, and in standard form, this is how it's written. So what was done to get to this form? What was the procedure? What's the technique? That's how you're going to, that's what that heading is about. So how do we write in standard form? Every number has a standard form, even though it is not shown. So for instance, you have 1 on this side. So when you see a number 1, you don't see a decimal point here, but it has a decimal point. So 1 is equals to 1.0. But because 0 is non-significant, we ignored it. It didn't have impact on the figure after all. So 1 is equal to 1.0. In a normal sense, it's 1.0, but because 0 is non-significant, it doesn't matter. It didn't matter, so it became just 1. 10 is also a number that has a decimal point, 10.0, but 0 is non-significant, so it's 10. Automatically, it was written as 10. 20 is also 20.0, that's a decimal point, but 0 that you have there after the decimal point is non-significant, so it was ignored. 346 has a decimal point after this significant, the last significant figure, which is 346.0. But after the decimal point, since 0 is non-significant, it was ignored. That was why you have 346 here. So you could write 346.0 or 346. Any of them is correct. Same thing with this part, same thing with this part, same thing with this part. You decide to write 1 as 1.0, it's still correct. You decide to write 10 as 10.0, it's still correct, because they all mean the same thing. Now, in standard form, generally, we move our decimal points. As for large numbers, we move backward and count the number of digits passed before getting to the first known 0 digit. So what we include, all to mean by that to get or to write a number which is in the ordinary form, in standard form, we just move the decimal points whether backward or forward. If we move the decimal points backward, that means we're going to have that means we move the decimal points backward in numbers that are large, and numbers that are small we move the decimal points forward. But generally, writing standard form simply means to move our decimal points. So if you followed when I said every number has a decimal point, if you take for instance you have a number like 13 ordinarily has a standard decimal point 13.0. So if this one is not in standard form as it is, even though it has a decimal point and 0, so standard form or writing standard form basically means to move our decimal points. So this number is large, that means we're going to move the decimal point backward. So the number of times we move this decimal point backward will give us the value of this figure in standard form. So, and usually the rule is you move the decimal point as many times as possible until it gets to the two numbers which are the last, or the first and the second, the first and the second significant figures. So you must move the decimal point until it gets to the first and the second significant figure, and you put it between those two numbers. So in this case, since it's the decimal point, the first significant figure is this number and the second is this number. So you move it until it gets here and then you drop it. So it will not be 1.3 times 10 raised to the number of times to make that movement, which was once, because formerly it was 13.0, and then you moved it until it got to the first and the second significant figure, and then you drop it here, so raised to power 1. So that's all there is about writing a number in standard form. If you take this number 346.0, this number ordinarily is in the ordinary form. So if you're told to write this in standard form, what do you do? Like I just explained, writing a number in standard form means movement. For large numbers, you move the decimal point backwards. So this is a large number, and in this video we are looking at very large numbers, and writing numbers that are in the ordinary form, large numbers in ordinary form in standard form. So what you do is you move your decimal point until it gets to the between the first and second significant figures, and you drop it there. So now back to significant figures. Significant figures are figures that are not zeros. So if you have 2, 7, 8, 2 is not 0, 7 is not 0, 8 is not 0, so we call them significant figures. So the first significant figure here is 2, the second is 7, the third is 8. So if you have, let's say 0, 2, 3, 4, we have 4 digits here, but 0, which is the first digit, is not significant. So the significant figure starts from 2, 3, 4. So every digit apart from 0 are significant. Okay, so if you have 2, 3, 4, 0, so in this case is 0 significant? Yes, so it's significant in this respect. But when you're moving your decimal points from here, so this 2, 3, 4.0, so when you move your decimal point from here, you move it until it gets to the first and the second significant figures, which is 2 and 3, and you drop it here. So, but in the ordinary sense, 0 in this case is significant because it's at the last point, it's at the last it's the last digit. But if 0 is starting a number, that 0 is not significant, and 0 after a decimal point is not significant, but 0 before a decimal point is significant. it has to the value of the number. Okay, so basically writing in standard form means movement of the decimal point. So in this case, if we move our decimal point in order to write this number in standard form, this will mean 1, 2. So the rule is let it be between the first and the second significant figure and put it there. So once you put the decimal figure here, it becomes 3.46 times 10. This 10 is it's an arbitrary notation. So you are going to raise it to the power. The power will depend on how many times that movement was made. So in this case, for you to be able to bring the point from here to this point where it must be, you made 2 moves, or the movement was done 2 times. So 1, 2. So it's not raised to power 2. That's how it is done. So let's look at the examples here, or let me read it again. So in standard form, generally, we move our decimal point full stop. As for large numbers, we move backward. That's what we did. We moved the decimal point backward and count the number of digits passed before getting to the first known 0 digit. That is 1. Take note that 1 is just 1. So 1.0 is press 1. That is 1.0 times 10 raised to power 0. Why power 0? Is it possible for us to have 10 raised to power 0 in standard form? Yes, it's possible. And this is the reason. Power 0 because of no movement. Remember, 1 and 1 has a decimal point. And if you are expressing a number in decimal point, it must, the number itself must be written in decimal form, where the decimal point is between the first significant figure and the next significant figure. So in this case, 1 is the only significant figure. So and in this form, in the form where it has a decimal point, there's no way you can move decimal point further. So 1.0 times 10 raised to 0, there was no movement. So there was 0 movement. That's what it implies. Then here 10 is equals to 1.0 times 10 raised to 1. So 10 is the ordinary form is 10.0. So if you move this decimal point backwards, that was only one movement that was done. So one movement backward, this will give us 1.0 times 10 raised to 1. So when we make this movement backward, we're going to have 1.0 times 10 raised to 1. So that's the way we get these figures. Look at this, 20 to get 2.0 times 10 raised to 1. Same one movement. Then 346 is 3.46 times 10 raised to 2. 2 movements backward. That was what I explained here. Okay, so let's look at these examples. This is express the following in standard form. These examples will buttress or reinforce the explanation I just gave earlier. So just follow through. If you have any difficulty, or if you are yet to understand or grasp the principle or the procedure on how large numbers are written in standard form, please pause the video or you start and watch from the beginning. Take your time, and if you have questions, draw them in the comments box. I will attend to them. So let's proceed. Solution number 1. 720 million is rated. So in this case, like I said, we must assume that these numbers are, regardless of how large they are, we have a decimal point. So in that decimal point, we will need to write this 720 million point 0. You will discover that even though there's a point here, and since here is 0, it does not affect or have impact on this number, because at a decimal point, 0 is non-significant. So either you write it like this or you write it like this, it's still the same figure. So, but it's necessary when you're trying to understand how to write large numbers in standard form, because you're going to make movements with the decimal point. So sometimes you're confused. So where is the decimal point coming from? Because when I started, I said you must move decimal point from a point where it was. So the first significant figure, or between the first and second significant figure, and drop it there. So you might be wondering, so where was that decimal point before it was moved? So this way it was generally every number has a decimal point. Once the number is given, whether it's 876, this is the number 9487, this is the number. At the end of this number, the decimal point, decimal point. So this is basic in understanding how to write large numbers in standard form. So task is to move this decimal point and take it to move it until we get to the first decimal point, sorry, the first significant figure, and drop it there. So at the end of the day, it's going to be between the first significant figure and the second significant figure. That's where it's going to be all the time. So in this case, if you move our decimal points, we're going to have 1, 2, 3, 4, 5, 6, 7, 8. We drop it here. That's 7.2. So these are the only significant figures. So 7.2, you need to decide to write 7.20. It doesn't matter. So 7.2 or 7.20 still. Remember that after the decimal point, 0 is not significant. So 7.2 times 10. So like I said, this 10 is an arbitrary notation. It must be there. So the power will be the number of times you make this move. You move the decimal point from here to this point. Let's get it. 1, 2, 3, 4, 5, 6, 7, 8. So that's raised to the power of 8. Let's be sure. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 7.20. So 720 million is 7.2. That's 7.20 times 10 raised to the power 8. That's the answer in standard form. Number 2, 4, 3, 6, 7. So 4, 3, 6, 7.0. We move the decimal point. 1, 2, 3. So that's 4.367 times 10 raised to the power 3. Number 3, 8, 2, 3, 900 equals to 82290.0. 1, 2, 3, 4, 5. 8.239 times 10 raised to 5. You would score that when we write this number in standard form, we ignored the zeros now because it's after the decimal point, because they are not significant. So that's the rule. So in this case, there's 1 0 here. If you want to, you can leave it, but it shouldn't be more than 1 0 after the decimal point, but it's still not significant. So I could as well leave 1 0 here, but I decided to not to leave it. So this is the general form, or the general way of writing it. Once you have zeros and you move the decimal point and place it here, therefore the zeros after the last significant figure is they are irrelevant or not important, so you can ignore them. Number 4, 5, 3, 7, 6 equals to 5, 3, 7, 6, 1, 2, 2, 5, 4, 0, 7, 6 times 10 raised to the power 2. Number 4, 5, 2, 0, 0, 0, 5, 2, 2, 0, 0, 5 equals to, so we move it from here. 1, 2, 3, 4, 2, 2, 0, 0, 5 times 10 is 1, 2, 3, 4, 10 to 4. So let's look at this number 2, 3, 0, 0, 5. If you look at it critically, you discover that the zeros are between a significant figure and another significant figure. So because of that, the zeros are significant. You don't ignore them. So when you move the decimal point from here, from 0, 1, 2, 3, 4, you don't say 2.3. You can say 2.3 times 10, it's still raised to 10 raised to power 5, but the appropriate way to represent it is 2.3005 times 10 raised to power 5. So you are not omitting the zeros because they are not significant. Rather, you're only omitting them because you are taking your figure is rounded down to the nearest two decimal place or so. But usually these zeros are significant, so don't ignore them. It must be part of the figure because they are between two significant figures. If they are the only digits after the last significant figure, and because they are zeros, in that case, since they are after the decimal point, then they are no longer significant, so you can do without them, which we did in this case. 6, 2, 5, 0, 0, 0, 0. This give us 1, 2, 3, 4, 5, 2.5 times 10 raised to 5. So exactly what I explained here. 2, 5, 0, 0, 0. So you discover that more after we make the movement, which is 1, 2, 3, 4, 5. Now decimal point is here. So the last significant figure is 5, which you have 2.5 times 10 raised to 5. Now we didn't write the zeros because the zeros are the last set of digits after our decimal point, and the last significant figure was 5 or is 5. So we can do without the zeros because since the decimal point is here and they are after the last significant figures, they are no longer relevant or significant, so we can do without them. But if they were between significant figures, we can't do away with them. We must write them or include them, except we choose to pick just the significant figures, the first and the second, and then still write it in standard form, raise it to the appropriate power. Number 7. Express 2 hours in seconds and put the answer in standard form. Well, we know that 2 hours in seconds will give us 2 hours. 2 hours in seconds means to find the equivalent of 2 hours in seconds. That will give us 2 hours. 60 seconds will give us 60 minutes, and 60 minutes will give us 1 hour. So that will give us 2. Right, so in 1 hour, it's equivalent to 60 times 60. So 2 times 60 times 60. And that will give us 60 times 60 is 3,600 times 2, 7,200. 7,200 seconds. This is the value in ordinary form. In standard form, we're going to move our decimal points 7,200.0. That's another way we can write it when we put it in the form that it has a decimal point. So we'll move the decimal point backwards 1, 2, 3, that's 7.2. At this point, the zeros are no longer significant. So 0.2. We make the movement 1, 2, 3 times 0.2 times 10 raised to the power 2 seconds. That's the implication. Number 8. So calculate 72 times 800 expressing in standard form. 72 times 800 is equals to, let's do our calculation. 872 times 7. 2 times 0 is 0. 2 times 0 is 0. 2 times 8 is 16. 7 times 0 is 0. 7 times 0 is 0. 7 times 8 is 56. 7 times 0 is 6. 5. 56 of 0, 0, 6, 7. 5. That's 5760. 57600. So our decimal point is here. So let's move it backwards. 1, 2, 3, 4. Put this here. So this is equal to 5.76 times 10 raised to 1, 2, 3, 4. 10 to the power 4. That's the value.